Let's first define monotonic functions. What does monotonic mean? What does
Singular.
monotonic? What's that?
Singular
How do you mean singular?
or like in sync or something.
No, not in this sense, not in calculus. Monotonic. Well, think if you have a monotonic sound, a voice, that's a voice that doesn't change. It's constant. When we talk about monotonic functions, that means functions that are doing the same thing. In this case, because now how it relates to derivatives. Derivatives define what? Since derivatives are rate of change, it also more so means slope. So monotonic functions are functions with the same slope on each open interval of a function. But let's think about it. There's only three slopes we can have in a function. What are they? One, the slope could be positive. If it's positive, what's happening there with the function? Then the function is doing what? Increasing. On the interval, starting from the endpoints. If the derivative is negative, that means the slope is negative. What is it doing then? The function is decreasing on the closed interval. And the third one is if the slope is equal to 0. What's happening there? Nothing's happening. Because there is no slope at that point. Then there is no change at that x. Because the slope is 0 at that point. It's a horizontal line. It's the vertex. Now, where does this happen? Can the slope be 0 at a point?
Yeah.
Is it at a point? Yes. Can it happen in an interval? Can the slope be the slope or derivative equals 0 on an interval, on an interval AB? Here's A, here's B. Yes, it can. If the interval AB is defined by the function f of x equals c by a constant function. So if that's the case, then it's a constant function. Let's look for an example. These are pretty boring without examples. Now, well, we'll discuss. Find the critical points of f of x equals x cubed minus 12x minus 5 and identify the open intervals on which f is increasing and or decreasing. Now, the critical points are the x values in which the derivative equals 0. The x values where the first derivative is equal to 0. Why are those called critical points? Because at that point, think about it. Let's see. If this is a maximum, what has to be true about the slope of the graph on both sides of that? Not decreasing. Yes. If this is a maximum, this has to be true. The derivative on the left-hand side has to be positive. And the derivative on the right-hand side has to be negative. Because it has to go up, then go down. So where it changes is your critical point. Conversely, if you have a minimum, then to the left of that point, the derivative must be negative, and on the right, the derivative must be positive. Remember, derivative is slope. So the slope is negative, it means it goes down. Slope is positive, means it goes up. So this means it goes down. This means it goes up. This means it goes up. This means it goes down. And if that's the case, as x always goes to the right, these critical points, the maximum, the vertices, are where the change happens. So, find the critical points. First step. Find the critical points. The actual x values are called the critical values. The critical point is the actual point location where the slope is 0, is the vertex. So the critical values we call the x values. So how do we find the critical values?
You
So what equals?
find the derivative and then set it to 0?
Take the derivative, set that equal to 0, because that's where we find our vertices. So for our function, we have f of x equals x cubed minus 12x minus 5. The first derivative is 3x squared minus 12. Set that equal to 0. Solve for x. Add 12 to both sides first. X squared equals 4. Square root both sides. So x is equal to what? It's a positive or negative. Very good. Whenever you take a radical of an even root, then you have to put a plus or minus in front of it. So we know the critical points are at -2 and 2, wherever the y values are at that point. So where is it increasing, where is it decreasing? So since this, we know that the derivative has to be 0 there, we know the derivative of this one has to be 0. So how can we tell if this is a max or a min? Take a value to the left of it. Let's say -3. Plug this value inside the derivative. Why the derivative? Because the derivative finds what?
Slope.
The slope. If it's positive, we know it's increasing. If it's negative, we know it's decreasing. So we have 3. -3 squared is 9. 9 times 3 is 27 minus 12 is 15. It's positive, so this is increasing. Pick a number between this next interval. 0. If you ever use 0, use 0. Plug that into my derivative. 3 times 0 squared minus 12 equals -12. So this is less than 0, so it's decreasing. So here we know we have a maximum at 12, at -2. Do we have to do anything for the -2 on the left-hand side of it? No, because this entire interval between -2 and 2 is decreasing. Everything between there is decreasing. So what's happening to the right of it? Let's pick 3. F prime of 3. 3 times 3 squared minus 12. 27 minus 12 is 15 again. So here it's increasing. So at 2, we have a min. But that's not what the question asked. That just helped us draw the graph of the function. It wanted us to tell us Where are the intervals? Identify the open intervals where a function is increasing, decreasing. So increasing. Where is it increasing? Nope,
-3 to -2.
nope. To where? And where else, if anywhere? Yeah, so here we put a union, +2 to positive infinity. Was at -2 and 2, that's where it stops. We know that here it's increasing, here it's decreasing, and here it's increasing. So this interval's increasing, this interval's increasing. And this interval is decreasing. It's decreasing between -2 and 2. Why do we use open intervals? Because think about it. What happens at -2? As opposed to increasing, decreasing. What happens at -2?
The slope is 0.
It's 0. It's the vertex. So we can't use -2 and 2 because those are zeros. There's nothing happening. So we look at everything happens on either side of those. That's why I use open intervals. Because if you use closed intervals, then you'd have to use that value, and you can't, because on every other point on this side, it's increasing, but at -2, it's 0. Any questions? Let's look at another one. Let's make up one. Let's look at that one. Tell me where it's increasing, where it's decreasing. We'll talk about the rest later. The first thing we have to do is what? Find the derivative, which is 3x squared minus 8x plus 9. Then what do we do? Set it equal to 0. Then what do we do? Now we factor, now we solve for x. Do we know any, this is a quadratic equation, do we know any formulas for quadratic equations? We can use there's what we're looking for here is what x values make it equal to 0, which in essence is the x-intercept in a quadratic equation. So A is 3, B is -8, C is 9. So negative of -8, -8 squared, 4 times 3 times 9. That's 8 plus or minus 64. 12 times 9. So what is this going to tell us? No, the y-intercept is 2. Well, we have an imaginary number, which that's not going to help us any. So what can we think about this? Are there any vertices here? If we were looking at x-intercepts of this function, we would be guaranteed, we know we have one x-intercept. We have to have one. Why?
Because it's an odd function.
It's an odd function, exactly. Both ends point different directions. But here, we're looking at, are there any vertices? Let's look at something here. Actually, I'll do it over here. To the power x to the power 3 minus 4x to the power squared. Oops. plus 9x. 9x plus 2. Ah. There are no vertices. There are no vertices. It's a continuously increasing function. So needless to say, my example was a bad example. If I would have gotten rid of a couple of these things, I got rid of that. Still wouldn't work. If we just did it this way. If we did this function instead. So the example I had originally, that's exactly what this says. Since this is imaginary, there are no vertices. I was going to ask you, is that possible? We just have one. So let's look at the one we had. F of x equals square root of x or cube root of x. Tell me the intervals where it's increasing or decreasing. So find me where it's increasing, decreasing. So the first thing we want to do is rewrite this one as x to the power 1/3, x minus 4. Multiply these out. X to the power 1/3 times x minus 4, x to the power 1/3. This is power 1. So 1/3 plus 1 equals 3/3. So for it's x to the power 4/3 minus 4x to the power 1/3. We have to first set it up so it's easily differentiable. So then we find the derivative. 4/3 x minus 1 is 1/3 minus 4/3 x to the power negative 2/3. So we took a derivative, set it equal to 0. Remember conversion. This is the root, always goes on the bottom. Can we combine these? Have to get a common denominator. They both have threes. Actually, they both have a 4/3. So we have cube root of x minus 1/cube root of x squared. To get a common denominator, what does this one need? It's over 1 right now. What is the LCD? The only denominator. So this one would need 3x squared over cube root of x squared. So we have cube root of x times cube root of x squared minus 1. You can combine these two. Cube root of x times cube root of x squared, since they're the same radicals, we can combine what's inside there. So x times x squared is the cube root of x cubed minus 1. Is equal to 4/3. Cube root of x cubed makes it just x minus 1. Top, we have 4x minus 1, 3 cube root of x squared. We'll leave that alone. Remember, set it equals 0. What makes it equal to 0? What's the only way a fraction can equal 0? Basic algebra. Pre-algebra. If the numerator, the only way a fraction can equal 0 is if the top is equal to 0. And the only thing in there that can make 0 is if x equals 1. Is there a value we cannot use?
A value that makes the numerator or the denominator 0.
What would happen there? What would happen here? If we did that, what would happen?
It would become undefined.
Ooh, so what does a slope of undefined look like?
A vertical asymptote.
No, not an asymptote. It would be a vertical line. But you're close, so yes. Because remember, our original function looks like this. It can't be an asymptote because can we use 0 in the original function? Yeah, if we plug in 0, the answer would be negative or 0 times this, it'd be 0. So it goes through the origin for sure. We know that at 0, the function is 0. But because at 0, the slope is undefined, we know that it's a vertical slope at that point. That has another cause next chapter or section. The only critical value we have is 1. At 0, we have a vertical line, so to speak. So what happens at 1? What happens? This is our critical value. What happens to the left of 1? We know it's 0, it's undefined. How about at negative 1? What happens there? If we put negative 1 inside here, negative 1 squared is positive 1, so that's going to stay positive. Negative 1 minus 1 is negative 2. That makes it top negative, so that makes it negative. Makes it less than 0. If we put 0.5 in there, we can't use this. At 0.5, we plug that in there. 0.5 minus 1, is it positive or negative? Negative. The bottom's always going to be positive, so we don't have to worry about it. So on the top, if we put 0.5, that's going to stay negative. So this is decreasing, this is decreasing, this is decreasing. So it's decreasing all the way to 1. What happens after 1? What happens at 2? Yes, but we can also have this. Yes, it could be a continuous, consistently decreasing function. But that's why I always have to check it. You would think that's true, that if this is decreasing, this has to be increasing, but it's not always the case. So at positive 2, remember, the only thing we look at is the numerator. 2 minus 1 is positive, so it's positive, so it's increasing. So from negative infinity to 1, it's decreasing. And then from 1 to infinity, it's increasing. So our graph, if we have to look at it, at 1 we have our vertex. So we put it back into our original equation. So at 1, cube root of 1 is 1, 1 minus 4 is negative 3. We have our vertex there. We know it's decreasing, has to be a vertical line there. The graph will look something like this. But here it's a vertical line here, and it goes on both sides. Let's look at this one. Find where it's open and increasing and decreasing. And this at f of 1, we have our vertex, which is our extrema. In this case, it's an absolute minima. See, all this stuff we can start defining and calling things now. So since our graph looks like this, we have an extrema. Do we have a maxima point, relative maxima or absolute maxima? No, because it keeps on going forever, ever upwards. So we're going to find the derivative first. Sure. So do you want to use the product rule or you want to distribute it and then take them separately? How'd y'all do it? Okay, well, it doesn't matter to me. They both work. So f is x squared minus 3 ex. The derivative is 2x. Derivative is ex. So we have 2x ex plus x squared minus 3 ex. We can factor out an ex, so we have x squared plus 2x minus 3. E to the x can never equal 0, so we set this equal to 0 now. E to the x can never equal 0, so that's out of the question. It's in, because the e to the x graph looks like this. So the only thing we can do is factor the other part. Since the second sign's a minus, that means the signs have to be opposite. Since they're opposite, we look at the bigger number gets the first sign, which is positive. What times what equals 3? When we subtract them, we get 2. 3 and 1. And 3 goes in the positive. So the answers are at -3 and +1. Those are my critical values. All right, so we know our critical values are at -3 and +1, and the function itself was x squared minus 3 e to the power of x. Yeah. And the derivative was e to the x, e to the x, x plus 3, x minus 1. So pick a value to the left of my critical value. These are my CVs. So at -4, at 0, at 2, those are the values we're going to pick. What happens at -4? E to the power -4 -4 plus 3, -4 minus 1. E is always positive, so it doesn't matter. So -4 plus 3 is -1, -5, it's +5, so it's increasing. At 0, e to the 0, 0 plus 3, 0 minus 1, that doesn't matter. So we have a +3, -1 makes it -3, less than 0, so it's decreasing. And the last one is at 2. E to the 2, 2 plus 3, 2 minus 1, 5 times 1 is positive, so it's increasing. So it's decreasing from -infinity to -3, increasing from -3 to 1, and increasing the rest of the way. So it's increasing it's increasing from -infinity to -3, and from 1 to +infinity. And it's decreasing from -3 to 1. The critical values, or the critical points, what they're looking for, are at x equals -3 and 1. That's what I was looking for. Find the function's local and absolute extreme values. So find extreme values. How would we do that? How do we find the extreme values? In other words, what they're looking, when they say extreme values, they're asking for the vertices. How do we find the vertices? Well, what equals 0? Well, we just did that. We took the derivative, set it, and we got the critical values. We set this equal to 0. And the only way it can use 0 is if x equals +3 and -1. -3, +1. Okay, so we have the extreme values here. What do we do with those? So the critical values are at x equals -3 and +1. At -3, is it going to be a maxima or a minima? It's going to be a maxima. And at -1, it's going to be a minimum. So we take these values and plug them into the original function. X squared minus 3 e to the power x. So at x equals -3, we got -3 squared minus 3 e to the power -3. So -3 squared is 9. 9 minus 3 is 6. E to the power -3. So that is my relative maximum or local maximum at -3, 6 e to the power -3. The relative minimum will be at, oop, I haven't worked it out yet, at 1. So it's 1 squared minus 3 e to the power 1, 1 minus 3e, negative 2e. So there's my relative minimum, there's my relative maximum, extrema points. And that's the end of that section. No, we have a question here. If you have questions, just spit it out. Don't. What's the question? You're looking lost.
No, I'm thinking about another question,
Okay.
another section.
So, yeah, once you find the critical values, plug them back to the original equation, now find the location. Those are the critical points. At that point, that's where it happens. That's it. That's it for today.